Okay, we are doing lesson 7.5, complex numbers. So first of all, we have our imaginary number I for imaginary. So technically we can take the square roots of negative numbers, they're just not real, so to speak. So we know I equals the square root of negative 1. Conversely, what you want to keep in mind is that then if you square I, you get the square root of negative 1 squared, which is just negative 1. So this is another property to keep in mind when we're using complex numbers. So first, we can simplify with these things. So if we look at square root of negative 16, we can actually split that into the square root of negative 1 times 16, because we're looking for i's here. And then we could split it square root of negative 1 times square root of 16, which will get us I times technically plus or minus 4, because technically the square root of 16, you can get 4 or negative 4, because if you square either of those, you get 16. So we'll write our answer as plus or minus 4i. Square root of negative 32, we'll start out the same way. I'm going to skip that first step here and go to square root of negative 1 times square root of 32. And now to simplify the 32 properly, let's make a little factor tree here, and if you can do this in your head, that's fine too. Basically what we're going to do here is look for perfect squares. So the first one I think of is 16, because we just used it. So what if we do 16 and 2? We're good here because we know the square root of 16 and 2 is prime. So I'm going to rewrite this down here, square root of negative 1 times square root of 16 times square root of 2. So this turns into I. Square root of 16 is plus or minus 4 again. Square root of 2 is just square root of 2. So when we simplify, we'll get plus or minus 4 square root of 2 times I. That order is conventional, what you normally see. Now 5i squared, well, technically this is going to be 5 squared, because this is where we can distribute that power, times I squared. 5 squared is 25, I squared is negative 1, so we'll get negative 25. So that's kind of the basic way you use I. Complex numbers in general, they'll be in the form a plus bi, where a and b are real numbers, so things you can plot, 1, 2, 3, etc. And I equals the square root of negative 1. So there's different operations we can do. If we have z equaling 4 plus 5i and w equaling 2 minus 3i, we'll simplify these. So first of all, z plus w. So if we do z plus w, we'll have 4 plus 5i plus 2 minus 3i. So 4 plus 2 is going to be 6. 5i plus negative 3i is going to be 2i. So our final answer is 6 plus 2i, because generally the I part comes second. And essentially what we're doing, you treat I like any other variable, like an x or anything else. The fact that it's I for imaginary doesn't matter, except I squared equals negative 1, whereas if you're squaring a normal variable like x squared, you just leave it as x squared. So that's the only difference. So let's do z minus w. So 4 plus 5i minus 2 minus 3i. 4 minus 2 is 2. 5i minus a negative 3i is like 5 plus 3i. So 8i, so we get 2 plus 8i. Moving on, z times w. So 4 plus 5i times 2 minus 3i. So 4 times 2 is 8. 4 times negative 3i is negative 12i. 5i times 2, 10i. 5i times negative 3i is going to be negative 15i squared. What happens though is I squared is -1. There's where I'd have you call it out if I was actually with you right now. So I squared is -1, so we'll end up with 8 minus 12i plus 10i minus 15 times -1. The negatives cancel. We end up with a plus 15. So we end up with, well, let's see, 8 plus 15 is 23. Negative 12i plus 10i is negative 2i, so we get 23 minus 2i. Z over 2. In a lot of ways, this is a little less, I don't know, algebraically taxing, I guess. So z is 4 plus 5i. Can divide by 2. I tend to call this the Hart method, so we can do 4 over 2 and 5i over 2. 4 over 2 is 2. 5i over 2 is just 5 halves times I. Could be 2.5i. Doesn't matter to me, because there isn't any rounding with 2.5. But again, we want it in a plus bi form. A pair of complex numbers like the previous examples, a plus bi and a minus bi, are called complex conjugates of each other. The complex conjugate of 5 minus 2i is just 5 plus 2i. So all that we're changing is the sign in the middle. The complex conjugate of -3 plus 2i is -3 minus 2i. So we don't worry about anything except that sign in between. And here's a theorem, complex conjugate multiplication. Again, I don't care if you know what the name is, but a plus bi times a minus bi always turns out to be a squared plus b squared. And I'll show you in these examples, but in general, you can just assume that too. So we are going to, in this example, express this as a plus bi form. So the way we do this, let's rewrite this because there's no space with where it's written now. 4 minus 3i over 5 plus I. And what we're going to do is multiply by the complex conjugate of the denominator. So let's even write that. Multiply by complex conjugate, I'm going to call it CC for now, of the denominator. And we can't just multiply by on one on the top or the bottom because then we're changing the value of the function. But we can multiply by 1. So we can multiply by 5 minus I over 5 minus I to kind of cheat the system a little bit. I'm going to add some parentheses to remember that technically they're separated. If we multiply the top, we have 4 times 5, which is 20. 4 times negative I, which is negative 4i. Negative 3i times 5, which is negative 15i. And 3i squared. And I squared is -1. On the bottom, so you can use this formula up here, but I'll show you why it works here. So if we do 5 times 5, we get 25. 5 times negative I is negative 5i. I times 5, positive 5i. And then I times negative I is going to be negative I squared. And I squared is -1. So if we simplify again, 20 negative 4i minus 15i is negative 19i. 3 times -1 is -3. Over, well, we have 25. Negative 5i plus 5i goes to 0. Negative -1, so the opposite of -1 is +1. Simplifying one more time, we'll get 20 minus 3, which is 17, minus 19i over 26. And then we'll do the Hart method. So our answer is 17 over 26 minus 19/26i, so that it's in our a plus bi form. A little bit tedious, but that's math sometimes. Let's do another. We'll multiply by the complex conjugate of the bottom, again, to make 1. So negative 3 plus 7i over negative 10 plus 2i, parentheses because we'll need them eventually, times negative 10 minus 2i, all we're changing is that sign in the middle, over negative 10 minus 2i. We go through and do this. Negative 3 times negative 10 is a positive 30. Negative 3 times negative 2i, positive 6i. 7i times negative 10, negative 70i. 7i times negative 2i, negative 14i squared. I squared is negative 1. And on the bottom, negative 10 times negative 10 is 100. Negative 10 times negative 2i is positive 20i. 2i times negative 10 is negative 20i. 2i times negative 2i is negative 4i squared, which is negative 1. So we have 30. 6i minus 70i is negative 64i. 14 times negative 1, or actually negative 14 times negative 1 ends up being a positive 14. Then we have 100. 20i minus 20i is 0. Negative 4 times negative 1 is a positive 4. So if we stop right here and look, this 100 plus 4 right here, that's actually our a plus b squared from up above, or a squared plus b squared. Because the a in a plus bi form for this one would be negative 10. Negative 10 squared is 100. The b is 2 or negative 2, it really doesn't matter, plus b squared. So we end up with 2 squared, which is 4, so there's our 100 plus 4. You can always do it by writing it out like this too, it doesn't really matter. So this equals 30 plus 14, which is 44, minus 64i over 104. So we can do Hart method. So we get 44 over 104 minus 64 over 104i. And then we have some fractions to simplify. Who doesn't love that? So 44 over 104, we can divide both of those by 4. So 11 over 26. 64 over 104, we can actually divide by 8. And if you didn't see this right away, that's okay. You can, divide by 2 a few times until you're done. 64 divided by 8 is 8. 104 divided by 8 is 13. So we end up with 11 over 26 minus 8 over 13.